Welcome to Argonne National Laboratory's Science at Work webinar series. Today we're going to discuss how hydrogen could replace fossil fuels and help the U.S. reduce carbon dioxide emissions to the atmosphere. We'll also explain the benefits of hydrogen use across energy sectors, specifically how businesses could produce, distribute, and store low-carbon hydrogen affordably and on a large scale. My name's John Harvey, and I'm a Commercialization Programs Manager here at Argonne. Just a few logistical notes before we get started. For a better experience, please check that your VPN is disconnected. If you're having any trouble with the technology, we recommend that you disconnect and re-enter. As you're aware, probably, your video and audio were automatically turned off when you joined the webinar. We do encourage you to ask questions using the public chat function. Because this event is so short, we probably won't have an opportunity to answer those questions live, but we will respond to them after the webinar ends. Finally, please note that today's webinar is being recorded and will be made available at a later date. Now I'd like to introduce our speaker, Dr. Amgad Elgowainy. Amgad is a senior scientist and group leader at Argonne, who leads the modeling and analysis of hydrogen use across various applications and battery electric vehicles at the lab. He's an expert in measuring all aspects of hydrogen life cycle emissions and economics of hydrogen delivery infrastructure. He created environmental and economic models that thousands of researchers use globally. Amgad, we look forward to your remarks.
Thank you, John, and hello, everyone. My short talk today, I will provide a background on what we do at Argonne to explore the opportunities for hydrogen deployment to decarbonize across sectors, as well as what are some challenges that could face such a deployment. Next slide, please. Yeah, some of you might be familiar with the Hydrogen at Scale initiative. This is a DOE initiative that looks at how hydrogen can play a central role to decarbonize across sectors. On the left side there, you will see the potential sources for hydrogen production. You see the renewables, you see the nuclear, you see some of the fossil sources with or without carbon capture and utilization and or storage. And you see hydrogen is in the center there that can help decarbonize. Also the transportation, which you see on the top right, the industry, you see the purple bubble there, and then you see the potential to work as a thermal energy carrier, whether by itself or through blending. Next slide, please. So when we look at hydrogen, we want to track, we know hydrogen is an energy carrier. It is a zero carbon energy carrier, one of the few zero carbon energy carriers. I mean, in addition to electricity and perhaps things like ammonia, hydrogen is a zero carbon energy carrier. However, how to produce hydrogen and tracking the energy to the primary source in nature will be key to understand the carbon footprint of hydrogen. So here on the left, you see potential sources. Again, you see the power, renewable, nuclear. I mean, these can be used to split water, produce hydrogen. You see the fossil, actually, these are predominantly today methane reforming of natural gas. I mean, there is the coal gasification, potentially with also carbon capture and or utilization. There is the biomass gasification. So all of these are potential sources for hydrogen. So this is what we call well to hydrogen production or well to gate. And this is an important phase in the life cycle analysis. Next slide, please. Then you see actually once you produce the hydrogen, how it can be used to decarbonize across sector. On the top right, you will see the direct use of hydrogen in transportation, mainly through fuel cell electrochemical conversion of the chemical energy and hydrogen into power to power the different vehicle classes and vocations. you see the potential to pair hydrogen with a carbon source such as CO2 to synthesize fuels. And this will be more like drop-in fuels or for blending with existing fuels. You'll see the upgrading of oils, whether it is a bio oil or a different source for oil, waste oils, or even petroleum oil. Hydrogen plays a major role to desulfurize, deoxygenate, and produce the fuel properties according to standards. And then you see the purple bubbles again, the potential of hydrogen to produce low carbon or green ammonia, to refine metals, to provide chemicals. And then again, at the bottom, you see the direct use of hydrogen for heating and the power applications, including the blending in natural gas pipelines. So when we look at well to gate and then gate to end use, actually then we cover the entire life cycle and then we understand the potential for decarbonization. Before we leave this slide, I mean, in the middle, you see hydrogen is at the center. So packaging the hydrogen, moving the hydrogen is another key stage in the life cycle, and I will talk about that separately. Next slide, please. So what we do is that we try to look at what is the potential demand by application, where are potentially these markets, current and the future, what is the carbon intensity through looking at the life cycle greenhouse gas emissions, and looking at the cost of making the hydrogen and the cost of the end product that you see on the far right as a sensitivity to the hydrogen cost that might be produced from the different sources, and then try to figure out at what break-even hydrogen price we can break even with the incumbent. Next slide, please. So in the center there, I mentioned the hydrogen packaging and the movement. And this is really a major stage in the life cycle, and it has a significant economic impact. So on the left here, you would see the gaseous way of moving hydrogen. You could compress it, put it in pipeline. Usually, if you have a very high throughput, a pipeline and maybe large geologic storage will be warranted. You can push that directly to end use. If you have distributed locations with a smaller demand, you could have a terminal, you could load tube trailers and move it, and then your end use could be vehicles or otherwise. On the right there, you see the different pathways moving liquid hydrogen. So as soon as you produce, you can liquefy. And once you liquefy, you get a very high energy density that you can move even more economically. So you could also have a terminal and liquid tankers that can move hydrogen to different end-use applications. Typically, the tube trailer will carry up to a ton, maybe 1.2 tons. The cryogenic tanker will carry up to 4 tons of hydrogen. And then pipelines will be warranted if you have some significant scale. Of course, it depends on the throughput and the distance to evaluate the levelized cost of pipeline and geologic storage on hydrogen bottom line cost. Outside of these, on-site production and the pairing production with end use could be another option. Next slide, please. So how we evaluate the potential and also the opportunities and the challenges, where are the cost drivers, where are the hot spots for emissions. So we have the techno-economic models you see on the left here. This is the hydrogen delivery model. We have a derivative of these for fueling fuel cell vehicles for different applications. And it is a bottom-up tool that is available publicly at the link you see at the bottom of the slide, where we start with market demands, understand how much hydrogen need to be moved. You could pick the mode, delivery mode, and then put your financial economic assumption, and then the model will size the infrastructure, will optimize certain components, and based on component costs we got from vendors, you could evaluate the levelized cost of hydrogen delivery. On the right here, we show the life cycle analysis model known as GREET. GREET stands for Greenhouse Gases Regulated Emissions and Energy Use in Technologies. And again, this is also a public model you can download on the bottom right link there. And the GREET evaluates energy use by source, looks at greenhouse gases, criteria, air pollutants, and water consumption, which will be an important factor if we evaluate hydrogen production through water electrolysis. Next slide, please. So I give one example on life cycle analysis, one example in techno-economic. Here we look at the life cycle analysis. This is the carbon intensity of well to gate, like this is the left portion on the first slide I showed, in kilograms of CO2 equivalent per kilogram of hydrogen. And here you see some selective pathways of interest. The first one is the baseline. The baseline is steam methane reforming, or SMR, hydrogen production. Typically there you will see hydrogen in the ballpark of 10 kilograms of CO2 per kilogram of hydrogen, depending on how much steam you produce and the credit you allocate really to the steam, and depending on the natural gas upstream, methane emissions, transportation distance, and the activities in the fields, whether it is really natural gas or shale gas. Next, you see another significant source of hydrogen today, mainly in the Gulf area, the cracking plants, ethylene cracking plants. I mean, once you crack really the NGLs, you have a significant byproduct hydrogen that is typically a stranded acid, but it is really combusted for process energy, but this could be purified and sent to the merchant markets. You see the SMR with CCS, what is called the blue hydrogen. You see that in the ballpark of 3 to 4 kilograms of CO2 per kilogram of hydrogen, with the major impact there on the upstream natural gas supply. So this will include the methane emissions upstream, include the transportation distance, and include the recovery and the processing of the gas. Biomass gasification is another pathway that can provide low carbon hydrogen, since the origin of the carbon in the biomass is biogenic. Byproduct hydrogen from chlorine plants is another important pathway that provide a lot of low carbon hydrogen to the market today. And in many cases, that hydrogen is being vented. So utilizing that waste stream, potentially waste stream, could be another source of a low carbon hydrogen. Of course, biogas from landfill or animal waste or wastewater treatment is another low carbon source of hydrogen, again, because the carbon there is organic, it is not a fossil source. Then we have the solar wind electrolysis. This is zero carbon if you look only at the fuel cycle, and then the nuclear, which has a very small footprint, whether we do the high temperature electrolysis or the low temperature electrolysis. And the small footprint there is attributed to the mining, recovery of uranium, transportation, and then enrichment. So these are activities with a small footprint. Next slide, please. Here we show how we pair. This is an example. So we did that for all the bubbles you have seen in the first chart across applications. So here I show one example. This is the ammonia production. On the left here, you see the life cycle emissions for gray ammonia, typically from SMR of natural gas. Today, it is roughly about 2.5 tons of CO2 per ton of ammonia, CO2 equivalent. While if you produce hydrogen, produce ammonia using a zero carbon hydrogen, you virtually eliminate all the emissions. But usually that reduction in emissions, that decarbonization potential, come at a cost. So what is that cost? This is what you see on the far right here. So you will see gray ammonia is in the ballpark of $300 a ton. Now, how, if you produce green ammonia, at what cost that might be? It is very sensitive to the green hydrogen price, I mean, or the low carbon hydrogen price. So if you have, your hydrogen is at $1, you break even with gray. So, but this is a tall order, big challenge to produce a low carbon hydrogen at $1, which is similar to what is being the cost of producing hydrogen from SMR today. If you double the cost of hydrogen to $2, then suddenly you jump into $500 a ton. If you move hydrogen to $5 a kilogram, then you are talking about $1,000 per ton of ammonia. And then we compare, really, we say, well, what is the cost of avoided carbon emissions, and try to do that as a metric. So we do that for other applications, but with that, I think I will stop here. I mean, I give you a feel of what we do. Most of our publications and the models are publicly available, and I will be happy to answer questions. Back to you, John.
Great. Thank you, Amgad. That was a really great talk. It looks like we've got time for one question before we let everybody go. So Looks like the first one that I have is, what are the major challenges in realizing hydrogen's potential to decarbonize applications across the energy sectors?
Thank you, John. So, as I mentioned, there are opportunities, but also challenges. And in the previous slide, I just showed that producing hydrogen at $1, this will be consistent with the DOE goals. I mean, $1 per kilogram in 1 decade. So if this is realized, it will be a game changer. Actually, it can really just open up the potential for hydrogen use across sector. We see that number, the dollar per kilogram, is also the break even for metal refining for synthetic fuel. But getting really to that level is the main challenge, and there should be R&D really, and the developing supply chain and the getting the scale to come close to that dollar per kilogram. The other challenge, of course, is in the infrastructure. I mean, and the infrastructure, I mean, can be deployed and be also economical, such as what we see in the Gulf today. In the Gulf today, there is a significant pipeline network for hydrogen. There is 2 major caverns there. So once you build the scale, infrastructure will have a good value proposition. The transition really to that larger scale is the key, and this will be enabled through some creative R&D, developing a scale, and of course with some public support.
Great, great. Thank you again, Amgad. Really appreciate it. And thank you all for attending our event today. I want to remind you that we will send written answers to the questions. I've seen the chat really going well, so exciting to see that. So we'll definitely send written answers to any questions that came in via the chat, along with a recording of Amgad's talk, and the links to the sites that he had discussed as well. If you have any questions or would like to learn more about how to partner with Argonne, please reach out to the email at the bottom of the slide there, partners@anl.gov, and we'd be happy to talk to you. So that includes our webinar. So thank you, everyone, and have a great day.